Hello friends, today we'll be talking about and discussing about 5G optimization, which is a very interesting topic for network planners, network optimization engineers, RF engineers, radio engineers, and the people who are working in RAN domain. So let's start what we have in this session. Here are the few subtopics which are very important for the 5G optimization, and we are covering these topics. So these are 5G basic concepts, why we need advanced antenna system, and network rollout and optimization process, and the procedures which are important, drive test KPI, and how we have to tune those drive test KPIs and what we can do on the parameter level to improve the KPIs. This would be like basically we'll be focusing on 5G NSA, because most of the market around the world are like focusing on non-standalone configuration and doing their rollout on a non-standalone configuration. So the basic approach would be to do an optimization for NSA, and the next would be like important events in 5G, important 5G parameters, non-standalone network KPI, and 5QI services which are being added on in the existing LT, and optimization techniques for EU-TRAN network dual connectivity, or we can say NR-NSA. And we'll be covering categorically for different KPIs like accessibility, retainability, integrity, and mobility for ENDC and NR-NSA optimization techniques. And then in last, we'll be covering as a whole summary and highlights what we have studied in this whole session. So here we have some 5G basic concepts, like this is a true advanced heterogeneous network where we can do cell dimensioning very dynamically. We can use LT plus NR as a dual connectivity. We can use other technologies as well, and we can use software defined network functions can be implemented through software defined network. We can use network slicing to implement and give services to different types of applications, like ultra low URLC, ultra low latency applications. We can basically move the network function location on the basis of network slicing concept. And as we know that 5G is very ultra reliable, we have to give a high rate of reliability in terms of the network availability, and also we have to give very low latency for ultra low latency applications and critical communication, which could be around 0.5 millisecond for URLLC applications in downlink and uplink. We would be having massive connections. It can be around 1 million connection per kilometer square. So we need to serve that requirement also. We'll be giving the services like enhanced mobile broadband with high capacity and high data rate, which could be around 20 Gbps in downlink and 10 Gbps in uplink. And we have to give mobility, which could be with zero interruption time. And this will be implementing through multi-antenna technology like massive MIMO, multi-user MIMO, single user MIMO, and you will be using advanced antenna systems. So let's move to the basic of NSA. So NSA is basically non-standalone configuration where basically we'll be implementing the first type of rollout with the 5G with interconnectivity of LT. So all the initial setup will be done on LT, like PLMN selection, system information sync, cell selection and reselection will be done on LT, tracking area update and paging and all those things will be done on LT. But for like capacity boost, we'll be having a 5G NR carrier which will be coming into picture once we need a larger bandwidth. So 5G capable UE will camp on LT, and it will be directed to B1 measurement which is basically for IRAT measurement and HO, and that B1 measurement will be done for the leg, NR leg, which will be set up once the SSB RSRP and SSB RSRQ met those threshold. So later on we'll be going into deep that what is SSB and how what are their threshold and what are the parameters related to that, and UE will be receiving the CRNK before the NR leg setup procedure is being done. So and if we want to release NR leg, so we can basically it could be because of radio link failure or some connection failure. So let's go into the some more important and deep. So here we have another concept which is like subcarrier spacing. In 5G we have 5G is basically an implementation of LT but in dynamic nature. So in LT we were having a fixed subcarrier spacing of 15 kilohertz, but in this 5G NR we can configure subcarrier spacing in our network, which could be done through parameter, and then that can be like 15 kilohertz, 30, 60, 120, 240, and this basically this whole calculation is done on the formula basis, and this is basically we have calculated the number of NR resource blocks for particular bandwidth and particular subcarrier spacing. So input can be A, which could be subcarrier spacing, and another input will be the bandwidth, and then we'll be calculating our number of resource block which we'll be getting in that configuration. So here is the a normal view of subcarrier spacing, how it is and what it is. In 15 kilohertz of spacing, like 1 millisecond slot, we have shown over here that it is like a more of larger slot of 1 millisecond. But as we go higher into the configuration from 15 kilohertz to 240 kilohertz subcarrier spacing, the slot size would be decreasing, and latency requirement can be met through these small slot sizes. As we can see, from 15 kilohertz to 30 kilohertz, the slot size is like came from 1 millisecond to 0.5 millisecond, and then again half to 0.25 millisecond, and then it's getting like decreasing. So basically with this mini slot concept, we can achieve those things in ultra low latency where we need very low latency. So here here there is a table where it's like we have taken a constant of 0, 1, 2, 3, 4, and the number of subcarrier spacing we can calculate accordingly, and how many slots will be there and all those. So basically it's like it could be in multiple of 2's, means 15, 30, 60, 120 and 240, and the slot size will be getting half every time. So this is basically for we have to do this increase subcarrier spacing in the band which is like greater than 6 gigahertz. So in that case we'll be giving more subcarrier spacing, the slot size will be decreasing, and we can provide the latency requirements which many of the ultra low latency applications require. So subcarrier spacing can be implemented through subcarrier spacing parameter, which is defined in the network, and the naming convention can be different in different vendors. And as subcarrier spacing changes, the slot duration changes, where it comes to the mini slot concept, where we can improve basically latency. So 5G NR basically support two types of band, or three types of band, we can say: low band, mid band and high band. And what we can see over here is like if we talk about the OFDM and symbols, then for subcarrier spacing less than or equal to 60 kilohertz, there could be like 7 or 14 OFDM symbols. But for subcarrier spacing greater than or equal to 120 kilohertz, there could be only one configuration of 14 optimal symbols. So it's like it depends on what subcarrier spacing we are defining. And link adaptation, it's like similar, which is working with similar to LT, like PDSEH, channel state information and rank indicator is reported to UE to decide what modulation scheme they want it want to use. And in uplink, PUSCH and uplink BMRS, noise plus interference and signal power is measured by G node B to decide the MCS. Cell range is one of the parameter where we can define the cell range of the NR cell, and that could also be basically depends on what we have done in our RACH sequence planning, and or we can say RSI planning. So 5G NR interfrequency handover are done on A3 measurements, and uh, NR like setup is done on B1 measurement, because for LT NR is like another technology, IRAD. So basically for NR leg setup, the second leg setup, once we have set up the LT leg, NR leg setup, we have to do B1 measurements, and uh, once the B1 measurements are done, we have identified the NR, which NR cell we have to go on, then we can basically do a setup for NR leg in second phase. So in next session, in next video, we'll be going for the NR radio frame, SSB, and beam management.